Hey everyone, so in this video we're going to be going over as many as I can out of these problems kind of from the book. Essentially there's some problems on energy, work, conservative forces, non-conservative forces. And so looking at this first one, it's saying X component of some force, so there's something getting pushed along in like the X direction, like a box or something, and the force varies as shown in this diagram below, and we're being asked to determine the work done by this force to move the object. And we're being asked about from 0 to 10 and from 0 to 15. So it's essentially saying from here to here, and then a second time from here to the very end is really kind of what it's asking us. And so what I did here kind of first and foremost is I kind of cut this up into different sections. And I cut up into different sections just to understand kind of what are we working with here. So we have like a triangle or a square, rectangle. We have a triangle, and we can see here that along the path, like the force is getting stronger and stronger and stronger, and then it's at this max for however long as it goes from 3 here to 7 here. And then it actually starts kind of diminishing and going back down until the force is 0 for a moment when the box or object is at 10 meters. And then the force becomes negative. So what the heck would a negative force mean? Well, if we're kind of assuming, as we usually do, that positive is to the right and up, this would actually mean that, our force for this first section is to the right, and for the second section would be going to the left. And looking at it to the left, it would get more and more negative until it's at its strongest from whatever this is, I don't know, 11.5 to 13.5, and then it would start getting smaller and smaller until it reaches 0 again at this 15-meter mark. And so how the heck do we figure out the work from this? Well, we need to note here that the y part of our graph is the force, and the x part is, x, the distance. And so kind of keeping that all in mind, we can recall that, work is just force parallel multiplied by the distance. And so it's moving in the x direction. The force that we're looking at is the x component of it, and so those are parallel to each other. And so really, if I want to find the work, all I need to do is find the area of the graph. That's it. It's actually that easy. And so looking at my first kind of chunk here, because it wants me to look at from 0 all the way over to 10, if I want to look at kind of that section, because that's what it's asking for part A, well, I would go ahead and just write that the work for sections 1, 2, 3, that's kind of how I'll just denote this whole little first area. Well, I'd say it's 1/2 the base, which would be 3 here. We're kind of at 3 here. So 3 meters times the height. Well, the height is 400 newtons. And then plus, now we have the area of section 2. That's just a rectangle. That's just length times width. And so we're going from 3 to 7. So the distance here is actually 4. So we have 4 meters times, and our height is 400 newtons. And then we have this last little section where it's, again, this triangle, and it actually is the same width. We're going from 7 to 10. So we have 3 meters, and the height was at 400 newtons. So I poke all this into my calculator, and I get that our work done was 2,800 joules. That's it. That's all we had to do. When it comes to part B, it's asking about now the work from the beginning at 0 all the way to the end. And so really what this is asking is saying, what is the total work? So the work that is totally done, total. And to do that, we just need to combine the area of this first kind of section with the area of the second section. And we can probably note here that, hey, since in the second area here, the force values are negative, we're going to have a negative work. So maybe we're going, what the heck does negative work mean? Well, it means that if we had, I don't know, some box, and the box was getting pushed by you over to the right for the first section of the graph, it means that eventually when it hits this kind of 10-meter mark, it means you're not standing on the left side and pushing to the right anymore. What it would mean is that the box is now kind of at this 10 meter mark here. And it means that you would now be standing here on the left side, and you'd be kind of pushing back against it, kind of resisting it, even though it would still be moving to the right, because it's still going to go from 10 meters to 15 meters. So it's still going to be moving to the right, but now you're kind of opposing it. So you're doing work in the negative direction is what that really means. And so if I want to find that total work, I would say that it's the work for sections 1, 2, and 3 combined, so added to the work for sections 4, 5, and 6. And we're going to find that, this work for 4, 5, and 6, that is a negative value. And so kind of getting rid of my silly little picture here, at least. There we go. Let's get rid of all this. If I wanted to do that, I would say, we know the work for section 1, 2, 3, it's already up here. We can just kind of plug it in there. Let's find the work for 4, 5, 6. So the work for 4, 5, and 6, that ends up being, and we just have two triangles and a rectangle again. So I'm going to have 1/2 base times height. So my 2 meters, and I'm saying kind of approximately 2 meters here. I'm really just kind of rounding and saying that, for convenience sake, we'll just kind of put it there. And then our height is this negative 200 newtons. And then we're going to end up having kind of something similar. We'll have 1.5 meters and then negative 200 newtons. And I'm kind of having to ballpark and estimate the x or the d distance values kind of here for our work equation. Work is force times distance. Plus, again, this last triangle, so 1/2 the base times the height, and that is a negative 200 newtons. And that ends up giving me negative 650 joules. So now I have this other one. I can really just go ahead and plug into this now and say, I now have 2,800 joules of positive work that I did pushing this in the x direction to the right. And then I'm subtracting the 650, or we could have rewritten this as plus a negative 650. It works out the same. Joules of work of me kind of resisting it. And the goal is to really just kind of have it so that I don't have to do any work when it's at this 15 meter mark. And so that ends up giving us 2,150 joules here for part B. Excellent. So now, question 19. Looking at 19 here, how much work is required? I'm not sure what even just happened there. I'm really sorry. That's odd. I don't need to know how to use the pen. There we go. So how much work is required to stop an electron, and we're given the mass of the electron, which is moving with some speed. So how much work do you have to do is essentially what it's asking here. And so maybe we have this little electron, and it's just like zipping and zamming over. I will tell you that this speed for the electron that they give us, that's 4.2 million miles an hour. This is a really, really, really fast electron. So we can put a little E minus, that's a symbol for an electron. And maybe here you're kind of standing here and you're like, whoa, what's going on? And you're like in this kind of, old school kind of cowboy position. You're like, whoa, you're like, halt, right? Halt. How much work do you have to do to stop this thing from like screaming in and slamming into you? So we want to stop the thing. That tells us that the final speed is going to be 0 meters per second. And we just really have to recall our work energy principle, which is from our previous page of notes kind of on non-conservative forces, work energy principle, things like that. And the work energy principle tells us, so work energy principle tells us that the change in kinetic energy, so the change in kinetic energy is equal to the work done. So essentially, you're changing the kinetic energy of the electron, so the energy of it is changing. Where is that change in energy coming from? It's coming from you. And so all we really have to do is note that, the work is equal to the change in kinetic energy. So rewriting that, the work is equal to, 1/2 mv final squared minus, because it's the change in, 1/2 m, the initial speed squared. And we want it to stop at the end. So that means that this whole term is 0 because the final speed, this final v, is going to be 0. So with that, we can kind of look at this and go, wait, it gave us the mass here. It gave us the initial speed. I can literally just plug into this now and kind of be done essentially. So the work is equal to 1/2 9.11 times 10 to the negative 31 kilograms, still getting some scientific notation here, times our 1.90 times 10 to the 6 meters per second. And that is squared. Don't forget to square that. That is a huge common mistake people make. And I get negative 1.64 times 10 to the negative 18 joules. So it's really not taking much work on your part to stop this electron, even though it's screaming along. And the real reason is because, well, its mass is so tiny. That's really kind of the giveaway there. All right, so 35 here we have Jane. Jane is looking for Tarzan, and she is running along at top speed. Her top speed apparently is 5.6 meters per second. You can multiply that by 2.2, I think, to get that in miles per hour. She grabs a vine hanging vertically. Okay, so we have Jane here essentially. So let me draw Jane really quick. So we have Jane here. Jane looks like all my other stick people apparently. No, we can give her some hair. There we go. That's much better. Now she looks a little more feminine, or maybe it's just to do with long hair. I'm not sure. And she's running at top speed, and she grabs this vine. So there's this vine then, and maybe the vine is kind of coming right along here, and it's hanging vertically. How high can she swing? Okay, how high can she swing upward? All right. So she's going to run and hit this thing, and she's just going to, she's booking it. She has all kinetic energy. She's at top speed. She's all kinetic energy with some initial velocity here. And then she's going to grab this vine, and it's going to swing upward at some point, and then she'll be up here along the vine at whatever this maximum height is that she's at. So maybe the vine swings up to here. Well, we would say then that from here to the bottom where the vine originally was, this is the height up that she gets. And at this max height, if you kind of swing up all the way, we know that this is where she has to stop to turn around. So this is all potential energy right here. All right. So what I can do then is I can say that, well, if she was all kinetic in the beginning, if it's all potential here at the end, I can set these two energies equal because we're not going to destroy any energy. That doesn't happen. There's no friction. There's no non-conservative things going on that are going to remove energy. There's no heating, anything like that. So we can just say that, well, the kinetic at the beginning is equal to the potential due to gravity at the end. I can just plug in now. Really, we're kind of done with the physics part of this problem. It's really just, can you plug in and do some algebra now? This is more of a math thing, really, instead of a physics thing instead. And it seems a little odd that we weren't given Jane's mass. But once we kind of get to this step right here, we can see, there's a mass on both sides. Those two cancel out from each other. And so if I'm trying to find out how high up she can swing, I need to get this delta y alone. So I'd have v naught squared, her initial speed squared, over 2g equals y, or so you could call it delta y. If you're saying that this is, 0 where she started, you're just going to be up some distance. If it was more she's already up 5 meters, we're going to go, okay, well, maybe she's at 15 here. Well, the delta y is going to be 10 meters. So I just like to call where we start 0, and it kind of makes life a little easier. We don't have to do that subtraction at the end. And so plugging into this, I'm going to end up getting a value of, or let's look, 5.6 meters per second squared over twice 9.8 meters per second squared. And that gives me 1.6 meters. That's how high up she gets. All right. So one thing I want to mention here is it also asks the second part, does the length of the vine affect your answer? Okay, let's think about it. Well, if we just have energy of one type becoming energy of another type, and we're kind of thinking about it, I don't see length anywhere in any of these equations. So this could be 100 miles long, or it could be 3 meters long. Either way, we're getting from this that, well, she's going to be up this much higher. It doesn't matter if it's this tiny rinky-dink little vine like this. It's just going to swing up really quick and she'll be at her max height. Or it could be some stupendously long vine and still swinging up 1.6 meters vertically. Well, it's going to have to be a much bigger arc, absolutely, but it's still going to go up whatever the two lines on our page. And so no, it turns out that the length of the vine does not affect the answer because there's no L anywhere in the equation here. So that's totally irrelevant. So we'd say the length doesn't matter. The length does not matter. She goes up 1.6 meters no matter what. Now, for number 39 here, it seems like we have some trampoline artists. We're given their mass, 75 kilograms, and they jump vertically upward. Okay, so if you're jumping, that means that you're going fastest the moment you jump, and you're going to go slower and slower as you come towards the top. And they jump with a speed of 0.50 meters, and we wanted to find out how fast is he going as he lands on the trampoline. And we're told the trampoline is 3 meters below. Okay, we're given this picture up here. We'll take a peek at that in a moment. And then part B actually says if the trampoline behaves like a spring and we're given a spring constant, how far does he depress it? So the trampoline is becoming depressed. Great. So looking at our diagram here, well, it looks like they're jumping up from the top, and so they have some initial speed here. That's their 5 meters per second. And typically, since they're moving, we would say that they absolutely have kinetic energy. But now, do they have potential? I would say yes, but it's actually a little bit up to debate depending on where you choose zero height to be. I'm going to selectively choose zero height to be right here along where the trampoline is. And I'm going to call this kind of my position where the potential energy due to gravity, so my UG, is 0. So if that's the case, then he definitely has kinetic and potential when he takes off right here. And then he's going to go up and up and up and up and up and up, and then he's going to come back down and hit the trampoline, something like that. And so at the top here, where he reaches it, kind of right here, well, he stops. He stops to turn around, right? And so right here, we're going to say that it's all potential energy. There's no kinetic. And then as he comes back down, 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 he's losing height until right here, he's going to hit essentially that 0, or maybe he comes down here. He hits kind of that 0 gravitational potential energy point. So what the heck, where is all the energy? Well, it must all be, I'm going to bring this up a little bit actually, right here. It must all be kinetic. But then we're saying that he pushes down the spring, so the trampoline, it gets stretched actually. And so it kind of stretches down a little bit more. And then at this moment, when the trampoline stops, it's all spring potential. And so really, what we're kind of being told here is we have all these different kinds of potential or kinetic energy, but since there's nothing non-conservative, there's no friction, there's no air resistance, we have all of the mechanical energies conserved. And if you remember back to some earlier notes, mechanical energies just means the sum of all of the potential and kinetic. And so it's the same amount. So if it was 100 joules here, it would be 100 joules here, it would be 100 joules here, and it would be 100 joules here. Now, it's not 100. We don't know what it is, but that's the idea behind it. So now, let's actually dig into this problem itself. and we want to find out how fast is he going as he lands on the trampoline. So we're really not caring about the spring part when the trampoline gets stretched. We're really just kind of looking at, well, we have this and this and this. How do I figure out how fast he's going when he hits the trampoline? Well, I very much so am going to have to use this one then, because this has kind of the speed embedded in it. And so the way that I would like to write this out actually is I would like to write this out in the way that we know the initial, actually I'm going to write it as the kinetic and potential in the very beginning. So I'm going to say start and start equals the gravitational potential at the top, and that equals the kinetic at the bottom. That's how I'm going to choose to write this. Maybe you chose to write it in words instead. You could say the energy at the beginning equals energy at the top equals energy at the bottom. That's the same thing. But since I want to end up finding the speed, I want to start using these equations as quickly as I can, really, is what I like to do. And so since we know the height right here, and since we know the speed right here, I'm going to choose to set this energy kind of time equal to this energy kind of time. I'm not going to use the potential at the top, and that's just because I don't know how high up he is. If I knew how high up he got, well then yes, I would totally choose to set the potential at the top equal to the kinetic at the bottom. It's only two things. I just set one equal to the other. But since we don't know the y value, this guy is not a good option. So let's kind of rewrite this now. So we have 1/2 mv naught squared equals, oh, oops, sorry, I already forgot my potential energy, equals mg and then delta y. And we know he goes up 3 meters, and then we have 1/2 mv squared. And so I look at these, everything has an m in it. So we actually don't even need to know that he's 75 kilograms. That actually doesn't do anything. And now we have 1/2, and I'm going to plug in for my speed value now. So we have 5 meters per second squared plus 9.8 meters per second squared. That's gravity times how high up he got, 3 meters, or how high up he started, really, equals 1/2, and then whatever our speed squared value is. So we have half of 25, so that's 12.5, and then we have like half of a little under 30, and we add those together, and then we double it, but then we're going to take a square root, and at the end of the day, when I do all of my algebra, I get 9.15 meters per second equals v. That is how fast he's going at the bottom. Excellent. So now let's look at part B. And I should have maybe put an A here, I guess, to start. Part B, if the trampoline behaves like a spring, how far does he depress it? And we're given the spring constant. We're given that K is 5.2 times 10 to the 4th newtons per meter. So it's a very strong spring, essentially. That makes sense. It's a human being jumping up and down on it. And now that we really know the kinetic energy at the bottom, we know this one, well, that energy must be the same as down here. And so we could what I would like to do is setting these two values equal to each other. Now we could have set the spring potential energy here equal to the kinetic and potential in the beginning, but again, I would rather use less things and do less steps of math. And so I'm just going to set those two equal. And something that's important to note is that he stops. He stops when the trampoline is stretched the most. It's kind of just like stopping at the top to turn around. You got to stop at the bottom down here when the spring or the trampoline is stretched the most, because then it has to like spring you back up. So really what we have here is that the kinetic at the bottom is equal to the spring when it's stretched at its max. And so I can really go ahead and rewrite this as my 1/2 mv squared equals, then we have 1/2 kx squared. And we're going to find out how far does he depress it? Okay, so the halves cancel on each side, half and a half. Those cancel out, great. And then I do need the mass, in fact, here, and we know the speed is this 9.15. So if I wanted to rewrite this, I would say then that mv squared over k, taking a square root, gives me x. And so now I want to plug into this value, and I'm going to move a little bit around here. There we go. So now I really just have, well, his mass is 75 kilograms. Our speed was 9.15 meters per second. We're going to square that, divide it by our spring constant, which is pretty huge, 5.2 times 10 to the 4th newtons per meter. And then we take a square root of that all. And at the end of the day, that gives me 0.347, or maybe just 0.35 meters is how far that gets stretched. So not very far, 35 centimeters. Okay. And maybe let's just bring this back down. Okay, 41. We have some projectile, and the projectile is fired at an angle of 45 degrees upward, okay, from the top of a 265 meter cliff, and we're given a speed, okay. What will its speed be when it strikes the ground below? So we just want to know how fast it's going. That's really all we're being asked here. And again, like in most instances in our class here, we get to ignore air resistance. Do not overthink it and keep adding in air resistance or overcomplicating it. It will make your life more challenging than it really needs to be, quite frankly. So first thing that I want to do is draw a little picture. And I just have my problem numbered. And then let's just sketch kind of a little cliff or something like that. So I have this cliff, there it is, and I have this projectile, it's going up at a 45, so that's kind of like right there. And this is the initial velocity, and we know that's this crazy 185 meters per second, really, really fast. And if that's the case, just like we did in Unit 1, I would say that there's some angle here. We're even told the angle. And so then we know that this is like the x component of the velocity, and that this is like the initial y component. And the initial y component is going to change. It's going to get less and less as it goes up because gravity pulls down on things. But this x component is not going to change because we're ignoring this air resistance. And so we know, or we can assume, that when it hits the ground, the potential energy due to gravity is zero. Like the ground is where there's no height. So we'll say that. So now if that's the case then, and we know that it's up some height y from here all the way down to there, well, I would say then that at the beginning it has potential energy due to gravity and it has kinetic, but when it hits the ground, it's just going to have potential. So this is going to be the potential at the top, and this is going to be potential, or no, this is just going to be kinetic, sorry. Kinetic at the bottom. So that's kind of the thinking through what the heck is going on here as far as kind of energy itself, all right? So now all we need to do is really plug in. So again, we have that our mg delta y plus 1/2 mv squared equals, and this is our initial velocity, and that equals our 1/2 mv squared at the bottom. Now, one thing to note is that this v right here, it's not the y velocity, it's just total velocity. We actually don't have to break it up into components here because kinetic energy doesn't really depend on direction. It's just how fast is it going. It doesn't matter if it has some crazy angle or doesn't, which is really nice. You don't have to do that trigonometry using sine and cosine like we used to have to do. So now again, I can see here M, M, those all cancel. Those are all gone, which is really nice and convenient. I can go ahead, I can plug in. I now have 9.8 meters per second squared times my 65 meter cliff plus 1/2 and its initial speed squared, 185 meters per second squared equals 1/2 of whatever the speed at the bottom is squared, okay? And so trudging through my algebra, multiplying this one, multiplying and making sure to square there, adding them together, and then multiplying it all by 2 ends up giving me a speed at the bottom of 199 meters per second is the speed at the bottom. Okay. Now, we could have done this a different way. We could have done this just like we did way back in our Unit 1. We could have actually done it that way. And I want to show that briefly just to kind of point out the difference, why the way we're doing this now is so much more advantageous. And so back in Unit 1, we would have had this horizontal, we would have had this vertical section. We would have kind of blindly written down a couple of equations. We would have said, oh, well, we know that the x velocity is equal to x over t. We would have said, fine, dandy. We would have had to use some cosine, and using cosine, we would have said that cosine of our angle would give us the x velocity over the initial velocity. We would have done something similar over on the right-hand side, and we would have said that sine of that angle would have given us the initial y velocity over just the total initial velocity. We would have had to deal with those two to actually kind of figure out what the heck is the initial y value. If we did that and we kind of plugged in to this, we would have ended up finding that our x velocity would be equal to 185 meters per second times cosine of 45, and then that would have been equal to 131 meters per second. We would have done the same thing with sine, and sine and cosine end up giving you the same values if it's a 45-degree angle, which we do have here, luckily. And so that ends up giving us just that the initial y velocity is also 131 meters per second. But then we had all these Unit 1 equations. We had that the final velocity is equal to the initial plus acceleration times time. We would have also had this final velocity squared is equal to the initial velocity squared plus twice the acceleration times the difference in y position. And then we had this final one that was this y equals the initial y plus the initial y velocity times time plus 1/2 the acceleration times the time squared. We had all these equations, and we had to look at this and go, well, what the heck is the speed at the bottom? Well, if you think about the path this projectile is taking, it's going to be going like this, and then it's going to be going like this, and at the end, there's going to kind of be not just it falling in a y direction, it's actually going to have, again, like a kind of x component to it. So it's actually going to have kind of some x component, and it's going to have some y component, and really there's a 90 here. And so we're going to have to find the x value and the y value, and we'll have to use Pythagorean's theorem to then find kind of this total y speed, or this total value for the vector that is the speed when it's down here. Not just the y, but it's actually both of them. So we'll have to use Pythagorean's theorem. So in the end, it turns out that we can totally use this second one because we know the initial y velocity, we know gravity is the thing that's accelerating it, and we know the difference in height. So we literally know every single thing except just kind of this this final y velocity. And so if we can find that final y velocity, we know the x we can plug into Pythagorean's theorem and we'll be done essentially. And so our final velocity squared is equal to then 131 meters per second squared. Again, I'm plugging into this. And so I need the initial y. We got it from using sine. Plus twice, and now gravity acts downward though, so that's a negative 9.8 meters per second squared, while this initial y velocity was going upward, so it's positive. And then times our difference in height. Well, where do you want to call zero, in all honesty? That's kind of the challenge here, to be totally frank about things. And so in our case, we want to say, I would say, just for convenience sake, that having it start with zero at the bottom would be really kind of the easiest thing. And so if it's starting at the bottom, then you're doing our final value is zero, and we're subtracting our initial, so 265 meters. And so I have a negative here and a negative here. Those are going to combine to make a positive. And so when I multiply these and I add it to this, and then I take the square root, I end up getting that our final y velocity, when it's about to hit the bottom, is 150 meters per second. So now, what the heck am I supposed to do? I have a y value, I have an x value. Well, again, since it's going to be moving at some angle down here, right? And we don't know what really the angle is here, but we know that there's just going to be a 90, so it's a 90-degree triangle. So we can, again, use Pythagorean's theorem. So my total velocity vector is equal to the x squared plus the y squared, and this first one should be squared. And so that becomes then 131 meters per second squared plus 150 meters per second squared. And so I do the math here, and then I take a square root of it all, and that gives me a velocity value of 199 meters per second. We literally got the same answer doing it the method we did in Unit 1. Now, I would argue to tell you personally that I think this method was a lot more work. I think this method was a lot more complicated compared to just saying, oh, the energy at the top and the energy at the bottom are equal, and then just plugging in. This value was literally, it was write it symbolically and then put in equations and then put in math and then have an answer was really all that we did here. And this one on the left, this took a heck of a lot more thought. So I would actually kind of point out or encourage you to kind of see the value and really appreciate this new way that we're kind of able to go about solving problems, because it is pretty incredibly convenient. I must say, I really must say. So now let's look down at number 41. This one should be a lot quicker. We're not going to go through and have to deal with anything in the Unit 1 kind of style of things, but we have a slide, and we kind of have the slide has a loop-to-loop in it, and there's a small mass M. It slides without friction. That's great. So there's no non-conservative forces. That's nice. And it slides along the loop. If the object is to remain on the track, even at the top of the circle, okay, we're given a radius r. From what minimum height h? Okay, what minimum height h is really what it's asking here. Must it be released? Okay, so what the heck is going on here? Well, again, we have to note what happens when it's at the very top here. When it's at the very top, gravity's acting down. So in essence, gravity is acting towards the center. So gravity is our centripetal force, right? Gravity is the thing that's going to be keeping it going in a circle. And if it's just barely to remain on the track, essentially there isn't going to be a normal force because it's asking for the minimum height to just barely remain on the track. So if it was screaming through, if this like little box or whatever was like screaming through here and going really, really fast, it would be pushing against the wall of the track really hard here. And there's going to be some normal force pushing back. And so if it's going really fast, gravity isn't going to change. And so what's in charge of keeping it on the track and not crashing through? Well, then it would be, in fact, a normal force to assist. But if it's going slowly enough, the car or the box here isn't pushing into the track very hard. And so really, once it gets to the top here, gravity is going to be the only thing doing any work or kind of acting to keep it going in the circle. Now, aside from that, we should really note that when it's kind of at this top position, I guess it's up here, or maybe it started up here really, it's all potential. Now, when it's down here, I would say that it's all kinetic. And so what that means when the box is kind of at the top of the loop, well, it's both. We have potential and kinetic. And that really means, whether you're aware of it or not, that we chose to call kind of this height the line where the potential energy due to gravity is 0, in fact, okay? So for number 44 here, we get to go ahead and forget about friction. Yay. Forget friction. So what this means really is that mechanical energy is going to be conserved. Mechanical energy is that combination of kinetic and potential. And it just means that, oh, really, this is equal to this is equal to this. If we had friction, we'd have non-conservative forces. Well, that means that this value would end up being less than this because some energy would be dissipated and we wouldn't be able to get it back. But we are following conservation of mechanical energy. Just general energy conservation is always followed. And so since we're being asked to find what is the minimum height that it must be released. Okay, so we have a couple options here. I'm going to say that the potential energy at the top is equal to the potential in the loop plus the kinetic in the loop, and that's equal to the kinetic at the bottom. Great. So now what do I want to set equal? Well, we don't know how fast it's going, but in the problem here, we were actually given, maybe I didn't notice, we were given a height h. So since we kind of know an algebraic height h, I definitely want to use this because I can write out that potential energy is mgh, which is kind of nice. And since we're being asked about what is the minimum height to stay in the track, I want to look at the time when it's actually on going through the loop, really. So I'm not going to look at this part where it's at the bottom, at least not yet. So the way that I would go ahead and I would rewrite this then is mgh. I'm not calling this delta y anymore because they called it h for us. I want to stick to what they say. And now I have mg, and what the heck is the potential energy and what is the height when it's up here? Well, we're told it has a radius r. So if it's up at the top of the loop, it's gone up not one radius, but 2 radii, right? So I'd have 2r here in all honesty, right? And then I'd have plus 1/2 mv squared. And so nicely enough, we can cancel the m's on each of these, all right? Now we have gh is equal to 2gr plus 1/2 v squared, okay? But now I have to kind of mention something from earlier. We know that for the minimum height, because maybe the minimum height is actually like right here, right? Well, if you go up any bit higher than that, of course, the box is still going to make it through the loop. But any little bit higher here for the box, we're going to end up seeing that the box is just going faster and faster through the loop. We want the minimum, so that it's essentially the slowest speed and the lowest height that the box will make it through. And for that to be true, again, there is no normal force at the top of the loop. And so for that minimum height is what I'm going to write here. For min height, we know that gravity is the centripetal force. So that means then that I can write out mg is equal to mv squared over r. This is force gravity. This is our centripetal force. This is from last unit. Again, the masses will cancel, and I can end up rewriting this as g times r equals v squared, or if I just want to find speed, I would square root both sides. So now what the heck was the point of this? Well, the point is actually that I do want to leave it as v squared, and you'll see why in a moment, is that I can now take this and I can plug it in right there. So essentially, we had to look at the forces going on at the top to be able to get rid of this v thing, and now we just have everything in g's and r's and h's. So now I can go ahead and I can kind of rewrite this little starred equation here. I'll rewrite it as now gh is equal to 2gr plus 1/2 gr. Oh, that's convenient. That looks really nice actually now. So now we can go ahead and we can do a little simplifying. G, those all cancel out. And now we have that the height is equal to 2.5 r. That's weird. It's just a really clean static number. So the minimum height to get anything to go through a loop-de-loop, if you're ignoring friction, is always 2.5 times the radius. If you're going to Six Flags and you have like the perfect, most optimal roller coaster, maybe it has magnetic levitation or something, so there's no friction, all right, and air resistance is negligible enough that you can ignore that. Well, if you measured the radius of the loop you have to go through, times it by 2.5, that's how high up your roller coaster must be for you to actually safely make it. Kind of neat, right? Okay, so now look at the skier. We've actually already talked about this one with the skier, kind of starts from rest, goes through. So if you got this one, feel free to just kind of skip ahead through it, or I hope you've been doing that this whole time in all actuality. But let's keep going. So we have the skier. They go down a 20-degree incline. It's 100 meters long. So really we know the angle. We know D. We know how far the distance they're traveling is. And we're told a coefficient of friction. So we know mu, and we want to find out what is the ski's speed at the base of the incline. And then part B takes it a step farther and says if the snow is level, so that means it's flat, horizontal, and has the same coefficient of friction, how far will the ski travel along? Okay. And more importantly, it says use energy methods. We could maybe have gone ahead and used kind of some unit 1 stuff. But this one's saying use energy. Please use this kind of method. So looking at this, I'm going to draw kind of my little slant, my slope here. And we're told it's at a 20-degree. Now, this is exaggerated. This is like 40 degrees. But that's okay. So we'll just go kind of right along there. And there. We know that this angle, and we're told that it's 20 degrees. Great. And here is our ski. My ski is going to be pretty shoddy. Sorry about that. It's like a little boat. And let's undo whatever the heck that was there. And we know that the ski travels 100 meters, right? So we know that from essentially from here to here, it travels this 100 meters. So we know how far it goes. Excellent. Now, unfortunately, in this problem, we're told that we do have friction to deal with. So even though at the top, when it starts up here, it has to be all potential energy due to gravity, they say it starts from rest. So there's no kinetic energy there. And at the bottom, there's no more height. So we're kind of assuming the bottom of our slope here is 0 for height. Well, that means it's all kinetic energy there. Well, it's saying that since we have friction, this value of energy must be less than this value of energy. We've lost energy and it's gone to like essentially frictional heating. We've essentially, as the ski has slid down, it's warmed kind of the molecules, not just of the ice, but also of the ski itself as the ski kind of slides down along here because there's this coefficient of friction. So essentially friction is acting over this distance. So we have a force and a distance. That means we're actually doing some work. Friction is doing some work here to heat up these two materials themselves, which is kind of odd. And then we know that for the last section of it, part B, we're told it kind of goes some distance over the snow. And we know again that mu is this 0.090. Great. So how the heck can we do this? I want to look at kind of energy. They say to use energy methods, and so that would make the most sense. And so looking at this, I'd say the potential energy at the top has some relationship to the kinetic energy at the bottom. Now, if there was no friction, these two would be equal, but we have friction, so that's not true. That means the potential energy at the top is greater than the kinetic at the bottom. So how can I still make this an equal? Well, it has to be the kinetic that's at the bottom combined with the work that was done by friction. So I'm just going to put work friction here. That's how I want to really approach this, because that's where the energy's gone. We do not have mechanical energy conserved here. Mechanical energy is the potential and kinetic. We can't get all of that back. We have this non-conservative thing. So mechanical energy is not conserved in this problem. So what we can do, though, is we can rewrite this out as mg delta y, and then our 1/2 mv squared, and work is force times distance. So now we have the force of friction times d. Great. Okay, and we have no idea what the mass is. We're not told what that is, but we know g. We don't know what y is either. Y is essentially the height that the ski was up at. But since I know here my distance, and I know my angle, I could use sine. I could find y. Let's just do that right now. So sine of my angle would be y over d. We know d, we know the angle. If I plug in 100 for d and my angle as 20 degrees, and make sure your calculator is in degrees, you will get that 34.2 meters is y. So now we know y. Excellent. That was easy. So we know y. So really, I want to go through and kind of highlight some of the things we know. So we know g, we know delta y. We don't know the speed at the bottom. Oh, that's what they're asking us to find. So we don't know the speed at the bottom. We do know the distance, though, and we don't know friction, and we don't know the mass. So what the heck? So I'd say the next step is I would want to find friction here. And I'm hoping that if we can find friction, maybe figuring out m will be the last step, and it'll be pretty easy here. So to find the force of friction, we have to look at what's physically going on here. And so I want to kind of shrink this a little bit, kind of hide that away there. And so really, if we were to draw kind of our free body diagram, remember, we have forces acting on a slant here. And so really, we have the force of gravity. Since the ski is sliding downhill, I'm going to have friction going uphill. Okay. Now, aside from that, we also 100% have a normal force. So our normal force, if I zoomed in a little bit, our normal force goes straight up off the surface. Essentially, there's a 90-degree box kind of here between the normal force and the surface itself. And then lastly, we have these two components. We have this force perp, the perpendicular part of gravity, and that force perp is called that because it is also perpendicular. We have this 90-degree box between it and the surface itself. And then we have this force parallel. And that force parallel is called that because it is literally parallel to the slanted slope itself that is our incline. Those two point in the same direction. They're parallel lines to each other. And last but not least, this angle is also 20 degrees. Whatever this angle is, it's the same angle kind of in our free body diagram, which is very convenient for us. So now, the goal here is I want to find friction and then be able to plug in right here. And then hopefully the mass part will be easy. Maybe there'll just kind of be some convenient solution for us. Or maybe like we've done problems before, the masses cancel. So I'm hoping the masses will cancel is really what I'm shooting for. So now looking back at kind of our notes on friction from unit 2, I see that the frictional force is mu times the normal force. We know mu, it's 0.090, so that's nice. Now, looking at my picture, I see that my normal force, I'm going to rewrite this, is mu, but my normal force, what is opposing my normal force here? Well, my ski, since it isn't jumping up off the mountainside into space, and it's not accelerating through the slanted slope, that means that my perpendicular part of gravity and the normal force balance each other out. So I can essentially go ahead and rewrite this as force perpendicular. I've substituted normal force for the perpendicular force. So now I need to find that. I need to figure out what the heck that is. Well, luckily for me, I'm pretty good with my trigonometry, and I'm going to look here and say that cosine of that angle is going to give me the perpendicular force divided by the force of gravity. And so really at the end of the day, that gives me that Fg, which is the force of gravity, but I'm just going to rewrite that now as m times g times cosine of my angle is the perpendicular force. So really, now I can take this, I can plug it in right there. And we can rewrite this one final time as mu times m times g times cosine of whatever the heck our angle is. So now, whoa, we have some crazy thing that we can plug in for friction. And it does have a mass in it. So what I'm going to do now is literally rewrite my whole equation now with all the numbers in. I'm essentially just going to rewrite this. We've been battling with it to kind of figure out everything but v, because we want to find v, and now we have everything we need, and we're just going to plug in and simplify. So now I have m times g, 9.8 meters per second squared. How high up is it? Well, we figured that out. It's 34.2 meters. So 34.2 meters. That equals my 1/2 mv squared. We're trying to find v, right? Plus mu. Oh, what is mu though? Mu is 0.090 times the mass times gravity, 9.8 meters per second squared, times cosine of 20 degrees, and then we have to multiply it by d at the end, so it's going 100 meters. Whoa, a lot of like just stuff, but I see here there's an m, there's an m, there's an m, all those cancel out. So now I see a number, a number, a number, a number, a number, and a number, and a 1/2. So these are all just numbers. So I literally do have everything done and needed to be able to get the speed itself. So I went through and I just kind of combined the numbers on the left side and the numbers on the right side to try and kind of make my life a little easier. So I ended up getting something like 335.2 meters squared over seconds squared equals 1/2 v squared plus, and I think I got 82.9, and then this is meters squared over seconds squared. And so at the end of the day, when I subtract the 82 away, I'm going to then have 252.3 meters, well, not a 3, meters squared over seconds squared equals 1/2 v squared. I times it by 2, I take a square root, and at the end of the day, I get that the speed is 22.5 meters per second. Wow. Okay, so that was part A. Part A was the hard part. If that didn't make sense, or if you're like, whoa, I followed, but now I had trouble, I would pause here. I would recommend you actually look back at it and try and explain the steps to yourself. It will be of tremendous benefit to actually go and do that. But let's look at part B. Part B is saying, now that we know really essentially the speed down here, right? Now we know how fast it's going at the bottom. It's saying, how far can it go before the ski stops. How far will the ski travel? Well, at the end of its time traveling, it's going to be stopped because we have friction acting here. There still is some coefficient, so friction is going to be acting over some distance. And so I look at this and I see, oh, well, we're going to say, I don't know, maybe we stop kind of right here. And so right here, well, the kinetic energy is going to be 0, and it's down at 0 height, so there's no potential energy. So where the heck did all the energy go? Well, all that energy was essentially done by lost in the form of work done by friction, is how I would really say it. And so we want to figure out what the heck is this distance from here to here. We want to find really what this x value is. We could call it d as well. We already use d here though, so I want to kind of stray away from doing that. And so really, I would say then that our kinetic energy at the bottom, that's right here, the bottom of the slope, once it's just reached the bottom, that's equal to the work done by friction along this new section x. And so I'll rewrite that. I have 1/2 mv squared is equal to force of friction times, and I'm going to call it x now because we're not dealing with kind of the slope up top, right? And now, how the heck do I find friction? Well, I found it over here, but now there isn't this crazy angle anymore. So now my ski is literally just kind of chilling here on the slope. So there's my ski, something like this. And we see that if we look at the ski here, all that's acting on it, we have gravity, we have the normal force, and again, we have friction just kind of dragging it down, right? So if that's the case, I would go ahead and I would rewrite friction. I would say that this frictional force, I'm going to rewrite it over here on the side. Frictional force, well, we know it's mu times the normal force, but now just the normal force and gravity are equal to each other. And so I don't need to deal with sines. I don't need to deal with cosines. It's just mu times the force of gravity. Well, I'm going to rewrite that then as mu times m times g. So that's all I need to use for my force of friction. So really, we're going to rewrite this equation now with friction plugged in. So I'll plug this in right there. So let's get a little more space. And so I would write this all as 1/2 mv squared equals, and now we have mu times m times g times x. And we want to find how far does it go. So we want to get x alone is really kind of the goal. And now I have an m on both sides, so I can cancel that. I can do a little algebra now. I can say that v squared over 2 mu and g, I just divided by mu and g on both sides, equals x. And now since we know the speed from part A, and if you didn't get part A, you could have just made up a number and still done part B is kind of the idea. That's what I would hope you would do on an AP exam at least. Then we can plug in our values. We have 22.5. We're going to square it. We're dividing it by, and then in kind of all this together, there's 2 times 0.090 times 9.8. That gives me an x value of 287 meters, something right around there. And I do make some algebra mistakes every once in a while, so let me know if you think I made a typo or something like that. And now for this last question, the very last one here. Yikes, this is maybe taking a little while. So we have this mass of a wood block. It's firmly attached to a very light horizontal spring. When I say very light here, that means you don't need to worry about the mass of the spring itself. So the spring essentially has no mass. And it's shown in some figure. I don't have the figure here. We can just kind of draw or sketch it a little bit. And it's noted that the block spring system is initially compressed 5 centimeters, and then it's released, and it stretches out 2.3 beyond equilibrium before stopping and turning back. And so we're being asked here, what is the coefficient of kinetic friction? So more or less, we essentially kind of have this scenario. This is kind of what reading that has put into my head. We have essentially some system, and there's some spring, and connected to the spring, we have just some box. And my box had an equilibrium point. Maybe the equilibrium point was, let's use purple. There's the equilibrium position. And let's say that it was kind of squished back 5 centimeters. So I'm putting a 5 centimeters here. That really means that from equilibrium to here is 5. And unfortunately, though, it only stretches out to 2.3 centimeters. So really, I'm saying 2.3 because the difference from here to here is the 2.3. And here it stops, they tell us. It stops before turning back. It stops and turns back. So thinking about this all, we know that when the box and kind of system and everything was compressed, something like this, way down to here, it was all spring potential energy. And then it's speeding along, and then right here, when it's at equilibrium, there's no energy in the spring because it's relaxed. And then as it keeps moving on and on and on, well, now we're stretching the spring, we're storing more energy in it. So now there's energy stored again here. But we can see that it didn't go as far as it was compressed. So what does that mean? What is actually going on here? Well, we've lost some energy. We lost some energy due to friction. They're telling us here straight up that like there's friction, and we want to find out what that coefficient is, okay? Now, the odd thing that I would like to point out is that friction has been acting from the beginning to the end here. So we really have to go ahead and look at this total length. This total length from here to here is what? That's what, 5 plus 2, that's 7.3 centimeters. Putting that in meters, because we need to kind of keep things in meters oftentimes, is 0.073 meters. That's going to be the distance that friction was kind of acting and doing work. So what I would like to point out is that obviously the potential energy at the end is less than at the beginning. It's not as far stretched as it was compressed. And so we can see that energy has been dissipated into work done by friction. So energy has been dissipated by friction is really what we're saying here. So we do not have mechanical energy being conserved. We don't have the kinetic and potential constantly saying the same value. We actually have some that is being lost. So the way I would write this all is that the potential in the spring before, I can write, sorry about that, folks, before is equal to the potential in the spring after. Normally this would not be true. Normally this one would be greater and the other one and the after would be less. But we can set those equal if we include the work that is done by friction. And so the way that we can do this is we can just plug in now. We really can just in fact plug in. Once we kind of got it figured out and understood, we can just rewrite this as 1/2 k, and then we have x, and I'm going to put like initial maybe squared equals 1/2 k, and then I don't know, maybe I shouldn't put an f here because then that's going to be friction. Maybe I'll just write friction, and we can use an f for final. X squared, actually, sorry, I'm all over the place today. There we go. Plus our work done by friction, and work we know is force times distance. So we'll do something kind of like that. We know D already. That's kind of convenient. We know the X initial. We know the X final. So really, all we need to do is find out what this frictional force is, because we know K, we know X, we know K, we know X, we know D. Really, I'm just trying to find out what is the coefficient of friction. So I need to find out something that's kind of embedded in this frictional force here. These cats are ridiculous. So now I can kind of plug in a little bit more. And if we remember and kind of think about friction, we know that force friction is mu times our normal force. But in the case of our box, it's just on a horizontal kind of spring, so horizontal table. We're going to rewrite this as mu times mg, because that's really the force of gravity, right? Because the force of gravity and the normal force are balancing each other out kind of in this scenario. So I'm going to plug in for all of my values now, and hopefully this kind of makes sense. I have 1/2, and then this 180 newtons per meter times 0.05 meters squared. I took this x value, I converted it to meters, equals 1/2 our spring constant again. And then we have this shorter distance. We have to square it though, once it's stretched, plus mu, and now we're given the mass, and now this is actually useful in this case. We do need this value, 0.520 kilograms times gravity. All right, so now we have all this. This is just friction. That's all this is. And then times the distance friction's been acting. Well, it's been acting the entire time from the start to the end. So now we have this 0.073 meters. So now really all we need to do is figure out what the heck this number is, what the heck this number is, kind of combine, do my algebra, do the algebraic steps here to figure out what the heck the number is. So I get 0.225, and now I have newtons times meters, because I had meters squared times newtons per meter, so I'm going to have kind of this weird unit here, equals 0.0476 Newton meters plus mu times 0.372 Newton meters. And that's what all these kind of units kind of married together become. So now I can just do a little subtraction of this guy to the left side, and then I'll divide by this thing that's stuck to my mu, and I end up getting 0.477 is our coefficient of friction. And so really the overall theme on these is, can you sketch a picture or come up with a good mental picture or look at the picture that's given to understand how we would represent the energy in kind of these before and after states? That's really what every single one of these problems has been. Can you represent the before and after? Then can we kind of plug in the values for each of these kind of terms that we know? How can we go about doing those? Then after that, it's really, now how can we get each of the things inside each term that we need to know to get the final thing that's being asked of us? And to do that, it's going to require your knowledge of forces like from Unit 2. It's going to require your knowledge of trigonometry. It's going to maybe even require your knowledge of projectile motion at times. And so that's the overall process on how to do all of these. Thank you for sticking around. Let me know if I made any typos, mistakes, errors. Do you have any questions?